going to do an electrolytic cell. So would this be a spontaneous or non-spontaneous reaction? So what does that tell us about the E?
It's going to be smaller or negative.
And how about the delta G?
Positive.
Because E and delta G have opposite meanings. What's happening at the cathode? Oxidation or reduction in an electrolytic cell.
Are they flipped? Or is it the same?
Well, what's our animal mnemonic?
So is it the same?
Yeah, so the key is that the animal mnemonics always work. We can always trust the animal mnemonics for any type of cell.
Electrolytic.
Red cat.
Yeah, so what would be happening here?
Reduction.
Right, red cat. That animal mnemonic always works. The cathode is always the site of reduction. So what's happening, this I meant to write this is the anode. What's happening at the anode then? Oxidation.
So I don't really understand like physically what the difference is. Like what is the difference like why you didn't draw a line through it? Is it like different?
What do you mean by a line through it?
A line through the metal? Is it because it wasn't drawn, you drew through it on the other side? Is that like a reason, or did you just not draw through it?
I'm not understanding what you mean by drawing through it.
Well, that.
Oh, I'm sorry, that's just my poor art. This is supposed to represent the aqueous solution.
Oh, okay.
And I guess I had a philosophical difficulty of should the aqueous squiggle cross the metal or not.
Oh, okay.
So yeah, there's no significance to the fact that I stopped the squiggle over here. I can extend the squiggle.
Sorry.
All I'm trying to show is that we have, say, a metal electrode in water, say. We had a metal electrode that's being immersed in our aqueous solution, for example. Okay. So let's see, this is oxidation. So what's happening over here? Loss of electrons or gain of electrons?
Gain of electrons.
Because that's the other animal mnemonic that always works. GER, gain of electrons is always reduction, and loss of electrons is always oxidation. So so which way are the electrons moving?
That way.
Towards the cathode or towards the anode?
Cathode.
So we can see that electrons always move towards cathodes regardless of the type of cell. Both galvanic and electrolytic, they have to move towards the cathode because the animal mnemonics tell us that that's always the source of reduction, gain of electrons. Do the electrons want to move over here?
In this case?
Yeah,
No.
in this case. No. So there must be some outside battery or power source that's forcing them to move. So this is kind of a symbol from physics for electric circuits for an outside battery or power source that's forcing the electrons to move. It wouldn't make sense to put in, say, a light bulb here. I wouldn't expect this cell to run another device. Instead, I need another device to run the cell. Right here, the cell is running this device, but in this case, this battery is running the cell. The cell needs energy put in to make it work. So here's the outside power source that's going to make this work. So you can just look at a diagram, a picture, and see whether it's supposed to be galvanic or electrolytic. If they put in an appliance, it's supposed to be galvanic. And if they put in an outside power source, that's because it's electrolytic. Or putting it another way, if there is no outside power source, it can only be galvanic. All right, now how would you decide who would go at the various places here? Well, I guess we could go back to the zinc and the copper in this case. Suppose we wanted to make an electrolytic cell using zinc and copper. Well, what should I put at the cathode then?
Would it still be copper? It's still reducing, so it's still copper.
Now, who do we want to put here now? The one who wants to be reduced or the one who doesn't want to be reduced?
It doesn't.
Yeah, otherwise we wouldn't need any energy to make that happen. All right, so who is it that doesn't want to be reduced here? The zinc. So it's the zinc that's now going to be over here. And what would be the half reaction that's taking place here?
Would it be just split?
Yeah. So what would that be?
So zinc 2 plus plus 2 electrons. The zinc solid.
Right. And what's the potential for that?
I think
Yeah, so what potential should I write down for that half reaction?
The negative 0.76.
Because it's reducing, so you want to.
So if you look it up in the table, you'll see negative 0.76, and that's a reduction potential, but this really is being reduced, so we can just use that reduction potential from the table. Okay, and who would we put over here? We put the copper. So what's the half reaction that's happening over here?
Copper solid yields copper 2 plus 2 electrons.
And what would be the potential here?
It would be negative 0.34.
Is that an oxidation or a reduction potential?
The positive 0.34 is the reduction one.
Good. So this one would be an oxidation. So again, the advice I would give you is that in your work, you should always label whether every potential is an oxidation or a reduction, even though unfortunately they don't do that in the book. Yeah, so what you said was correct. If you look this up in the table in the book has a number of positive 0.34, but that was a reduction potential. We want the oxidation potential, so we have to put in the negative sign. All right, and I would actually write that down. What chemists do is they just kind of keep the reduction potential in their head and they just flip the sign in their head, but that confuses me. It's less confusing to actually write it down with the flip sign on a piece of paper, so I don't have to keep flipping the sign in my head. All right, now how would we have known if this was a problem, who to put where? Well, we would go to the table, and we would look at the table and we would say here, who wants to be reduced more? Who wants to be reduced more, copper or zinc?
Copper.
The copper wants to be reduced because it has the positive reduction potential, but we need to put things where they don't want to be in an electrolytic cell. It's the copper that wants to be reduced, so I'm going to put the copper where it's going to get oxidized. And it's the zinc that, the copper wants to be reduced, so I'm putting it where it wants to be oxidized, and it's the zinc that doesn't really want to be reduced as much, so I'm going to put it here to force it to happen. So that's the kind of thinking you have to go through. You have to look at the half reactions and ask, who wants to be reduced, say, and then ask, am I trying to put things where they want to be or where they don't want to be? Well, for an electrolytic cell, we put them where they don't want to be. Okay, so I guess we might as well figure out what the cell potential would be here. What calculation do we need to do to find the standard cell potential?
Same thing. Add them.
So what number should I put in?
Negative 0.34 and negative 0.76.
We're still adding them, but we're adding two negative numbers. Now what would that give us?
Negative 1.1.
That's just the opposite of what we got before, right? But that makes sense.
Right.
What's the units on that? So the formula we used here was the oxidation potential at the anode plus the reduction potential at the cathode. Again, the book uses a different formula. The book just uses two reduction potentials and does a subtraction, but I think this is the more straightforward formula. But they're really equivalent to each other. Does it make sense that this came out negative? If it had come out positive, we would have known we did the setup wrong because we were trying to get something that doesn't want to happen. All right, and now I'll spare you, but we could do all the same questions that we did before. We could plug in E into these equations again and do all those different types of calculations. Now the delta G doesn't tell us how much work we can get out of the system. It's telling us how much work we have to put into the system to get the electrolytic process to work.